So we are continuing our previous GATE question solution program for the subject power systems, and now we are going to start with the previous questions of chapter 2, which is voltage control. So let us go into the previous questions. So this is question number 1. In a 400 kV network, 360 kV is recorded at a 400 kV bus. Now the reactive power absorbed by a shunt rated for 500 MVAR 400 kV connected at the bus is. So we will have to find out the reactive power absorbed by the system. And what is equation for reactive power absorbed? It is V square divided by X rated. V square divided by X rated. What is V? V is given as 360, and what is X rated? X rated can be found out with respect to 50 MVAR. So it is 400 square divided by 50 MVAR. So our reactive power absorbed is obtained as 40.5 MVAR. So what is our answer? Our answer is option D, which is 40.5 MVAR for question number 1. Now moving into the next question. A load draws 100 kW at 0.7 power factor lagging from a 3-phase 11 kV supply. It is decided to raise the power factor to 0.95 lagging using series capacitors. So you have to calculate the value of the rating of the capacitors that is required. So it is 100 kW at 0.7 power factor lagging from a 3-phase 11 kV supply. It is decided to increase 0.7 to 0.95 lagging. So the power factor improvement is to be done. So what is the reactive power old? It is equal to 100 tan cos inverse 0.7. So that means the reactive power is equal to 102 kVAR. We have to raise it to 0.95. So Q new equal to 100 tan cos inverse 0.95. So that means it is equal to 32.87 kVAR. So we will have to supply the difference of reactive powers. So what is the difference of reactive powers? It is 102 minus 32.87. So we will have to supply 69.13 kVAR of reactive power. So what is our reactive power? Reactive power equation is equal to Q reactive power is equal to V phase square divided by XC. Or also this equation can also be written to be XC is equal to V phase square divided by Q capacitance. Okay. Now what is V phase square? It is 11 kV system. So it is 11 divided by root 3 divided by 63.13. It is a 3-phase system. So we are going to find out the capacitive compensation requirement for single phase. So it is 69.13 divided by 3. So XC becomes equal to 1.75. This XC has to be converted to the value of capacitance C. So what is C? C is equal to 1 by 2 pi FC, or XC is equal to 1 divided by 2 pi FC. So capacitance is equal to 1 divided by 2 pi F into XC. Substituting the values, capacitance will be obtained as 1.82 microfarad. So what is the value of the rating of the capacitance required? The capacitance required is 1.82 microfarad. So this is the answer for question number 2. Now moving into the next question, question number 3. Series capacitive compensation in EHV transmission lines is used to reduce the line loading, improve the stability of the system, reduce the voltage profile, improve the protection of the system. So I have given you advantages and disadvantages with respect to the series compensation and also the shunt compensation. We have discussed the series compensation, shunt compensation points as separate notes while we were dealing with the chapter of power factor improvement. And also we discussed this with respect to voltage control also. Okay, so series capacitor and shunt capacitor arrangements were discussed with respect to star and also with respect to delta. So here you can see what is our synchronizing power equation. It is mod E mod V divided by X cos delta. If it is a 3-phase system, then the synchronizing power is equal to 3 times mod E mod V divided by X into cos delta. So you can see as the value of X increases, the synchronizing power increases. Okay, so what will be our option? We will improve the stability of the system, because for the P max and delta curve, which is the this is the power angle curve. With respect to the power angle curve, the Pmax of the system can be improved by reducing the value of the or increasing the value of the series capacitive compensation. Okay, so initially without a compensation, if this is the Pmax, which is Pmax 1, then with the compensation you will be able to increase the power delivery of the line to Pmax 2 because X is in the denominator. When X decreases, the value of the synchronizing power or the maximum power that can be transmitted through the system increases. So our option is it improves the stability of the system. So you have to always remember the series capacitive compensation mainly improves the stability of the system. Now for question number 4, moving into question number 4, a shunt reactor of 100 MVAr is operated at 98% of its rated voltage and 96% of its rated frequency. The reactive power absorbed by the reactor is. So here also the similar kind of question is being asked. So we will have to find the ratio of reactive powers with respect to change of voltage and frequency. So voltage is decreased by 98%. It is not decreased by 98%. It is operating at 98% of its rated voltage and it is operating at 96% of its rated frequency. Now we will have to find the reactive power absorbed by the reactor. So what is Q? Q is equal to V square divided by XL, we already know, or it is equal to V square divided by 2 pi Fl. So from which F is inversely proportional to Q and V is directly proportional to Q. So Q2 divided by Q1 becomes equal to an elaborate equation which can be taken down into the box of your notes. So it is Q2 divided by Q1 is equal to V2 by V1 the whole square into F1 divided by F2, and the ratio of variation of V and the ratio of variation of frequency is also given. So substituting that, and what is our actual Q1? Q1 is actually 100 MVAr. So substituting these values, you will get Q2 to be 100.042 MVAr. So it is 100.04 MVAr, which is option D for question number 4. Now moving into the next question, which is question number 5. The voltage phasor of a circuit. The voltage phasor of a circuit is 10 angle 15 degree volt and the current phasor is equal to 2 angle minus 45 degree ampere. The active and the reactive powers in the circuit. So we will have to find out the complex power P plus JQ, which is equal to VI. So it is given as 10 angle 15 degree and the current is given as 2 angle minus 45 degree. So it can be taken to be VI star. So complex power S is equal to VI star. So this 45 degree becomes equal to plus 45 degree. So 10 angle 15 degree into 2 angle 45 degree. It becomes equal to 20 angle 60 degree, which is also equal to 10 plus J 17.32. So the active and the reactive powers are to be separated. So what is active power? Active power is equal to 10 and reactive power is equal to 17.32 var. So P is equal to 10 and Q is equal to 17.32, which is option A for question number 5. So these are very simple questions coming from this chapter. Now moving into the next question, question number 6. A 3-phase 11 kV 50 Hz 200 kW load has a power factor of 0.8 lag. A delta connected 3-phase capacitor is used to improve the power factor to unity. So power factor is improved to unity from 0.8 lag. Okay, the capacitance per phase of the capacitor in microfarad. So what is the connection? It is connected in delta and it is a 3-phase bank. Okay, so we have to improve the power factor. So we are going to find out the load current because it is 200 kW load that is given and it is 11 kV. So it is 200 into 10 raised to 3 divided by root 3 into 11 into 10 raised to 3 into 0.8 angle cos inverse 0.8. So this is the load current. Okay. So the reactive part of the line current is to be supplied by the capacitor bank in order to have unity power factor. So this much part of the line current has to be compensated by the capacitance. Here you can see when it is 0.8 lag, it is a minus current which is equal to 7.8727. That is the reactive part of the current. So it has to be compensated because it is unity power factor that is required. So when it is unity power factor means there is no reactive part for the current. So what is the phase current that is to be supplied? So reactive part of the line current is to be supplied by the capacitor in order to obtain unity power factor. So it is 7.8729 divided by root 3 because it is delta connection. Because what is condition for star and delta? For a star connection, VL is equal to root 3 V phase and IL is equal to I phase for a star, and then for a delta, VL is equal to V phase and IL becomes equal to root 3 I phase. So for the current value, you will have a root 3 factor. Okay. So we are here calculating the current value and then we will be having a root 3 factor. So the phase value is equal to the line value divided by root 3. So line value divided by root 3, and what is IC? IC is equal to V divided by XC, and then from that XC is equal to V into 7.8729 divided by root 3. So from this we will be obtaining the value of XC, and when you are substituting XC into 1 divided by 2 pi of XC, you will be getting the value of C. So what is our capacitance value? Capacitance value is 1.31532. So what is the answer? It is 1.315. So it is 1.316 we will go. So for question number 6, our option is option B, 1.316. Moving into the next question, question number 7. A transmission line has equal voltages at the two ends, maintained constantly by two sources. A third source is to be provided to maintain the constant voltage equal to end voltages at either the midpoint of the line or at 75% of the distances from the sending end. Then the maximum power transfer capabilities of the line in the original case and the other two cases respectively will be in the following ratio. So it's a slightly lengthy question because it is a 2-mark question also. Okay. So a transmission line has actually equal voltages at the two ends which are maintained constant by two sources. So here we are having two sources injected at the ends. A third source is to be provided to maintain constant voltage either at the midpoint of the line or at 75% from the sending end. So then the maximum power transfer capabilities of the line in the original case and the other two cases respectively will be in the following ratios is what is the question. So what is our Pmax? Pmax is always equal to V square by X, or it is equal to mod E mod V divided by X. So here E is equal to V, so we can go for V square divided by X. When it is compensated at the midpoint, it becomes equal to P dash equal to V square divided by X by 2 sin delta by 2. So P dash max becomes equal to 2 times P max. When it is compensated at 75%, so that means X dash is equal to 0.75x. So it is V square divided by 0.75x, which becomes equal to 1 divided by 0.75 P max. So what will be our ratios? So the first condition is 1, and then the second condition will be equal to 2, and the third condition will be equal to 1.75. So it is equal to 1.75. So what is our answer? Our answer is option B. Okay. So this is a very good question because this question considers two factors. One injection at the midpoint and the other injection at a 75% distance from the sending end. So for your examination, any one of the cases can become, or they can change the percentage distance to some 60% or 80%. So you have to remember the way that we have done this question. So what is our ratio? Our ratio is equal to 1:2 is to 1 divided by 0.75, which is 1:2 is to 1 divided by 0.75, which is option B for question number 7. Moving into the next question, question number 8. A lossless radial transmission line with a surge impedance loading. A lossless radial transmission line with a surge impedance loading taking negative VAR at the sending end and 0 VAR at the receiving end, takes positive VAR at the sending end and 0 VAR at the receiving end. So if a line is maintained at the surge impedance loading, then it will not absorb any reactive power or it will not contribute any reactive power. it will have a flat voltage profile and unity power factor at all points along the line. So this is the answer. It has sending end voltage higher than that the receiving end voltage, so it will not happen because the line is maintained at a surge impedance loading. So when a lossless transmission line is maintained at a surge impedance loading, then it will always have a flat voltage, constant voltage profile and unity power factor at any point along the length of the line. So that is answer for question number 8. Moving into question number 9, consider the model shown in figure of a transmission line with a series capacitor at midpoint. At midpoint, the maximum voltage on the line is at the location. So we will have to find at which location the maximum voltage is happening. So the sending end voltage is equal to 1 per unit angle 0. So let us start doing this question. Here we can see what is voltage at point 2. Voltage at point 2 is equal to, what is point 2? This is point 2. So what is voltage at point 2? It is 1, because the sending end voltage is equal to 1 per unit angle 0. So it is 1 per unit minus 1 per unit into what is the current? The current is equal to 1 per unit. So it is 1 per unit into the drop that can happen is at 0.1 per unit. So it is 1 per unit minus 1 per unit of current into the reactance, which is 0.1 per unit. So that is the drop at point 2. At point 3, is the point which is after point 2. So there is drop here and there is also a drop here, but it is about the net reactance. So what is net reactance? Net reactance, here it is 0.1 and here it is 0.15. So it becomes equal to J 0.05 per unit. So it is 1 per unit plus, because here it was the reactive per unit, inductive per unit, so it was a drop. Here it is the net, because 0.1 is lesser than 0.15. So that means the net capacity effect will come. So it will turn to positive. So it is a sum. So that means there is an increase of potential here. Okay. At VP3. And when you are considering VP4, which is at this distance, there is another 0.1 here. So that means the net inductance becomes 0.2 and the net capacitance is only 0.15. So that means there also there is a reduction of voltage at 0.4. So at 0.4 also there is a reduction from 1 per unit. So this is a lesser value, this is a lesser value, but this is a higher value, because it increases 1 per unit voltage plus another 1 per unit into J.05 per unit. So the voltage is maximum at P3. It is lesser at P2 and it is lesser at P4. Okay. So what will be our answer? The maximum voltage on the line occurs at P2 or P3. It occurs at P3. It occurs at P3. So the voltage at P3 is maximum. So for question number 9, our option is option C. When you are considering P2, there is the inductive drop. When you are considering P3, there is the capacitive addition. And when you are considering P4, inductance again becomes larger than the capacitance, net capacitance value, and hence it also causes a drop. So here it is a drop causing a less value. Here also it is a drop causing a less value. Here it is an addition causing an increase of voltage. So the voltage to the point P3 will be maximum. So for a series compensation, we have also studied the theory. The voltage will be maximum at just the point after series compensation, because when you are going for a capacitive series compensation, the series compensator or the capacitor will act like a battery. So after the battery, your potential will be higher. But when you are going for a shunt compensation, the voltage profile will be uniformly obtained along the entire length of the line. So the compensation will be uniform along the entire length of the line for a shunt compensation, but for a series compensation, only a regional increase of voltage will be obtained. A zonal increase of voltage only will be obtained. So for this question, which is question number 9, our answer is option C. Moving into the next question, which is the 10th question. A 3-phase 11 kV generator feeds a power to a constant power unity power factor load of 100 megawatt through a three-phase transmission line. The line-to-line voltage at the terminals of the machine is maintained at 11 kV constant. The per unit positive sequence impedance of the line based on 100 MVA and 11 kV is J.2. The line-to-line voltage at the load terminals is measured to be less than 11 kV. The total reactive power to be injected at the terminals of the load to increase the line-to-line voltage at the load terminals to 11 kV is what is the question. So we will read the question once again. A three-phase 11 kV generator feeds power to a constant power unity power factor load of 100 megawatt through a three-phase transmission line. The line-to-line voltage at the terminals of the machine is 11 kV. Per unit positive sequence impedance of the line based on 100 MVA and 11 kV is J.2. The line-to-line voltage at the load terminals is measured to be less than 11 kV because there is a drop happening due to the J.2 reactance. Total reactive power to be injected at the terminals of the load to increase the line-to-line voltage at the load terminals to 11 kV is what is the question. So we will have to provide a compensation for the drop. Now, mod V of S is equal to mod V of R is equal to 11 kV. The per unit impedance of the line is equal to 0.2 per unit. Now impedance of the line equal to per unit impedance into base impedance. Okay. So what is actual impedance of the line? Actual impedance of the line is equal to per unit impedance into base impedance. What is base impedance? Base impedance is equal to base kV divided by 100 MW. So we have obtained the value of the reactance of the transmission line as 0.242 ohm. Now active power at the receiving end is equal to 100 MW. Now what is PR? PR is equal to mod Vs mod Vr divided by X into sine delta. So substituting all these values, we will be obtaining the value of sine delta. So this is the equation with respect to the real power. And with respect to the reactive power, this is the equation of QR, which is equal to mod Vs mod Vr divided by X cos delta minus Vr square divided by X. So here in this we know all the values. So our QR value is obtained to be minus 10.1 MVAR. So power factor is to be kept to unity. So we will have to find the value of power factor, that is to be what is the reactive power that is to be injected into the system. So total reactive power that is to be injected into the terminals of the load to increase the line-to-line voltage to the same value of 11 kV is what is the question. So we have obtained that the existing reactive power on the line is equal to minus 10.1 MVAR. So we will have to compensate to minus 10.1 MVAR. So how much reactive power is to be injected? We have to inject 10.1 MVAR. Okay. So the value of reactive power that is to be injected into the line is 10.1 MVAR because we have to compensate for minus 10.1 MVAR. So what is the value of the answer? It is 10.1 MVAR. So answer is option B, which is equal to 10.1 MVAR for question number 10. So that is option B. Moving into the next question, which is question number 11. A balanced delta connected load of 8 plus J6 ohm per phase is connected to a 400 volt 50 Hz 3-phase supply line. If the input power factor is to be improved to 0.9 by connecting a bank of star connected capacitors, the required kVAR of the bank is what is the question. So here the value is given. So we will have to improve it to the power factor to 0.9. So what is the net reactive power that is injected into the system? It is P1 into tan phi1 minus tan phi2 divided by 3 times 2 pi f V phase square. And we are going to find out the value of P1 because P1 is equal to 3 V square L divided by Z into cos phi1. And VL, V phase is equal to VL divided by root 3. So VL we will be obtaining as 400. So we have obtained VL as 400 and Z is equal to 8 plus J6. So mod Z is equal to 10. That can be substituted. And then we will have to find the value of phi1. So what is phi1? Phi1 is equal to tan inverse x by r. What is the value of x? X is equal to 6 and r is equal to 8. So it becomes phi 1 is equal to tan inverse 6 by 8, which gives cos phi 1, and then cos phi 2 is to be improved to 0.9. Okay. So we have obtained cos phi 1, cos phi 2, P1 is also obtained, V phase is also obtained. So directly we will be able to substitute all these values into this expression of QC, because QC is equal to P1 into tan phi 1 minus tan phi 2 the whole divided by 3 into 2 pi f V phase square. So substituting tan phi 1, tan phi 2, P1 and V phase square, we will be getting the value of QC as 10.2 kVAR, 10.2 kVAR, which is equal to option B for question number 11. So we will go with 10.2 kVAR for question number 11. So my dear friends, you have to check out each and every question the way that we are doing these questions. If necessary, you have to write down these equations again and again and again. Mark these equations are very important, because these are not simple theory equations. These are equations that will enable you to do a problem in the shortcut method. Okay, so that is about question number 11. And now we are moving into question number